So with that, I would like to introduce our presenter for today, Austin Coates. Austin runs both the sales engineering team and the sales operations teams at L3Harris Geospatial and has over a decade of experience in algorithm development, custom software solutions, and product management. He has led multiple remote sensing teams and has experience working in secure environments with the Department of Defense in government facilities, including NASA Jet Propulsion Laboratory, and for fast-paced startups like Farmer's Edge. His work has mainly been focused around multispectral and hyperspectral work. His publications have been featured in remote sensing of environment and remote sensing. And he's also my manager, so I'm very happy to be here to sort of usher him in for this talk because he's pretty fantastic. And with that, he's going to be talking about widening the spectral processing aperture with ENVI and open source tools. Austin, please take it away.
Thanks so much, Megan. So yeah, hi everyone. As Megan said, I'm Austin Coates, and yeah, I'm pretty excited for this one today. So if you can't see me on camera, here's a gigantic photo of me as well as my contact information. So yeah, reach out if you have any questions. All right, so getting started. So kind of this is the agenda that we'll run through today. I'm going to talk about a simplified analysis workflow. Actually, I'll back up and kind of set the stage a little bit. So the intention of this presentation and kind of the storyline that I wanted to follow when putting this together was, say you've just attended an amazing conference such as Spectral Sessions, and there's a bunch of really, really cool things that you saw, and you go back to your office or wherever you do your work, and you're thinking, man, I would really like to implement some of the things that I've seen, but maybe I use this software suite and it was written in that software suite, and I really like this piece over here and I just want their algorithm. So how do I get it all together and how do I put it all in one place? And so that's kind of the example that I want to walk you through today. So I'm very partial to ENVI. I use it for a whole host of things, including things that it was never intended to be used for. And I think it's just great. But just like everything, on occasion, there's stuff that's not in ENVI that I really want to give a go at. And so I'll reach out, I'll get some code, and then I go to run it. And ENVI has this amazing thing that's the Python bridge. So it allows you to connect ENVI to Python and the outside world. And so that's how I kind of broaden my spectral aperture is I run custom code through that. And so I'm going to kind of step you through the process of, let's say you went to a conference, you reached out to a researcher, said, oh, I loved what you did. They sent you some code. You're going to go give it a shot on your own. How do you do that? So starting off, I'm going to talk about a simplified analysis workflow, so kind of the steps that you would go through to go from raw data all the way up through a finished product. Kind of the entry points. So let's say you're using ENVI or IDL, and then you also want to use some Python. So how do you get them to play together? Some example code on how I did that, and then also we'll go through some questions. So let's take a look here. So starting off, so usually you've got your data exploration. So you probably have an image, you've downloaded it, you bring it up. So I usually do it in ENVI, pop it up. I look at the spectra, I look around, I'm like, oh, it looks like a tree, looks like some grass, maybe there's a car, the spectral profile looks right, or oh, maybe it looks like this, so probably it's in radiance. And so you do a little manual interpretation of your imagery, and kind of cruise around, get a lay of the land. The next bit you're going to do, maybe some pre-processing and preparing your data to be analyzed. And so maybe that's some atmospheric correction or some co-registration, band alignment, anything you need to do to get the data to be ready to have some math done on it. And then the next part is going to be your data processing steps. So that's where you really start to extract. So you start to pull out the information that you're interested in that image or in that spectra, and you're trying to get at it. And so this usually happens behind the scenes. There isn't kind of a visual representation of this. You just pass the data in, something happens, and then you get a result on the other end. And last but not least, your results. So you get those results back, you want to validate them, maybe you want to make some tweaks, you want to start this process over again, final QA, QC, or some product generation. So these are kind of the 4 steps. So you get your data in, you pre-process it, you do the hardcore math on it, and then you make a final product. So in talking with a bunch of our customers, this is kind of the workflow that a lot of different people use. And when I myself use open source tools, or even when some of our customers use open source tools, they usually will do the math side on the open source world. So not saying that ENVI can't do all these pieces, but maybe there's a really specific thing that somebody has created that you want to try out. And so they're going to do it over on this right-hand side, the open source side. So in kind of talking with people, we find out that, yeah, they do data extraction, some results and validation with ENVI and IDL, and then maybe they do a little pre-processing and some full data processing with open source tools. So I got the handshake in the middle because they play well together. So you can pass your data around, you can get your results back, and you can visualize everything in one place. Hold on. Got something in my throat today. All right, entry points. So how do you make these things work together? So I kind of see it as let's say you're just starting out. You have ENVI, you know how that works, and then you got this Python code. And you're like, how do I get them together? What do I do here? So got ENVI. The main way to get code into ENVI is through IDL, and so that is our proprietary language, and it makes it really easy and nice to extend ENVI. So anything it's available in ENVI, or almost anything that's available in ENVI, is also available in IDL in kind of a coding environment. And then IDL also has the Python bridge. So you can do two things. So you can call out to, or you can write your Python code inside of your IDL interpreter, and I'll show an example of that. Or you can have IDL call out to your actual code. So like maybe you have a module on the outside and you just want to write one line of code and then go call out to that. We can take a look at that as well. And so once again, there's other ways to work with open source code. So you can work with C code inside of IDL. You can do different like spawn commands, but all of that's a little outside of this presentation. Today we're just going to focus on Python because it's super ubiquitous. All right, so inside of ENVI, the two main ways that I interact with kind of this code outside of the ENVI IDL land is through either the modeler or generated task interfaces. So these are kind of graphical representations of the code in which you've brought in. And we'll take a look at that. So this is kind of the environment that you're looking at, though. So as a user, I might build a model that would use some ENVI tools that would run through IDL, call my open source code, my Python code over here, and then run everything back, and then I would see the results in my display. So let's take a nice look at this and see how a real world example would go. All right, so we have this super simplified scene here. And what we're gonna do today is we're gonna look at methane detection workflow. So you have an aircraft that's flown over. It has a spectrometer on it, and it's collecting information about the targets below it. And so I come from a vegetation remote sensing world where I mostly work in reflectance. So reflectance is when the light bounces off an object and comes back. But before the light gets to that object, it has to be transmitted through the atmosphere. So jump the gun on that. So the light can come from your light source, so usually the sun. It will be transmitted through the atmosphere, and then it will go down and hit your target and be reflected back. And so if you've ever heard of surface reflectance, that's what this is. Light's coming through the atmosphere, hitting your target and being bounced back. So usually we want to get rid of any kind of things that are happening in the atmosphere. And I had talked about it earlier with pre-processing. So you do atmospheric correction to get rid of that. So you just get surface reflectance. So that's what's happening on the ground. However, today we're going to be looking at methane. So we're going to be looking actually at the stuff in the middle of the atmosphere. And so we're going to be looking at absorption. So that is the light coming from the sun and then hitting the target being our methane particulate, and then being absorbed by that, by that gas. And so the way we're going to do this is I'm going to follow along this amazing lab that these two gentlemen, Dr. Philip Dennison and Dr. Marcus Foote, put together while Marcus was at the University of Utah. So I just wanted to say a huge thanks to both these gentlemen for putting this lab together. And it fit in perfect to my storyline because essentially I had ENVI, I wanted to do something. They had this amazing code in Python, and I'm like, oh wow, I'll just call out to this amazing lab, this amazing code that they have, and run it through ENVI. And it worked out great because I get to use the visualization tools that I am comfortable with and I like, but I still get to use the algorithms that they put together. Also, if you're interested, this lab and kind of these steps that I'm going to be running through here are a simplified version of this paper that they helped author along with several other people. If you are interested in a really, really amazing methane detection algorithm, this paper is a great read. It's really, really fascinating. So give it a read. All right. So the workflow that we're going to go through today is we're going to look at ENVI and the different pieces of ENVI. So we're going to read in an image and then kind of look at the spectra within that image. So this is very much in the like kind of data visualization piece. So it's kind of that first bucket. And yeah, do it in native ENVI. And then we're going to call out to some open source tools, and we are going to run through a couple of different pieces of code inside of these open source tools. So we will convolve an unit absorption spectrum, run a match filter, and then also run a column-wise match filter so that we can then get destriping. So the imagery that we're going to be using is Avris next-gen imagery. It's a hyperspectral imager that has many, many bands. So we'll take a look at it. But then once we have processed our imagery, then we'll bring it back into ENVI and we will take a look at the final results, and then we'll do a little cleanup. So let's check out block one here. So inside of ENVI and taking a look around at our image. So many of you are probably familiar with the ENVI interface. This is what it looks like here on the right-hand side. I'll actually pull it up here in a second so that we can kind of dance around in it. But to give you a little background on the imagery that we're going to be using. So the scene that we're going to be seeing, so it's actually that kind of strip over there on the left-hand side of the screen, or on the left-hand side of the ENVI screen. That is a 2019 Avris next-gen scene over the Permian Basin. And this is an area in which produces approximately 38% of the US's total oil production, as well as 17% of the natural gas production. So yeah, and also I want to call out here too. So the spectra on the image, you can see that is in radiance. So I talked a little bit about surface reflectance, which is something that I'm more comfortable with, but we're using radiance today because we want to make sure that we're looking at the atmosphere. And usually when you get to surface reflectance, you have removed the atmosphere. So just as a little side note, when we're doing this work, we're going to be working in radiance instead of surface reflectance. So, all right, let's pop over to ENVI and we'll take a look at this spectra. All right. So here is the scene that we were looking at before. Once again, Avris next-gen scene. We'll take a look at the spectral profile inside of here. So the darker areas, this is vegetation. These kind of lighter areas, these are well pads. And yeah, you can kind of see. So kind of that first step in the workflow, just taking a look around, getting a lay of the land, looking at my spectra, seeing what I see. Like, oh, okay, this is my area. And so what we want to do now is to see, are any of these refineries producing methane? And if so, what's the concentration look like? And let's get a visualization for that. So the first thing we need to do though is we need to have a representation of the methane in which we're going to try to pull out. So the spectral signature. So we're going to do that by bringing in a spectral profile of that methane. So, Spectral Library Viewer. Let's open this up. All right, so this is what we're going to go after. And so this was generated by looking at different concentrations of methane within a modeled atmosphere and seeing how the variations in methane concentration would vary the amount of absorption in these specific wavelengths. So you can see the wavelengths along the x-axis and then the absorption along the y-axis. So this, though, however, has lots and lots and lots and lots of bands in here. And Avarice, though it is an amazing spectrometer, it does not have as many bands. So we need to kind of reproject the data into the same data space as the Avarice scene. So let's take this and let's do just that. So inside of our IDL prompt, we wrote a little piece of code here. And so this piece of code will allow us to take in an image as well as our spectrum. So just like what we saw before. So once again, the image here and the spectrum. And then we will run it inside of this Python script. So in here, this just says, I'm going to create a program and these are going to be my inputs. And then this pulls out the information that I need. So I need to know the full width, half max, the center of each one of my bands, the spectrum that I'm looking at, and then the values, the wavelengths of that spectrum. And then this is the Python code that I'm actually going to run. So I wrote it directly in the program here. So because I wrote it this way, you got to make sure that you maintain your spacing appropriately. So since it's still just Python code, Python is very interested in spacing. And since it's kind of a weird way to write it, but it essentially is just one long string. You have to put these new line breaks in here so that when it interprets it and runs it inside of Python, it says, oh, okay, I'm going to have a new line, and my new line is going to say sigma equals raster full width half max divided by blah, 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 blah. So I would use this if I'm just going to write only a very, very few amount of lines of Python. It's just kind of like a quick way to get in and get out. So I could have recreated this in IDL. However, it was already written in Python, so I didn't have to even worry about it. I just got to copy and paste and do a little bit of formatting, and I was off to the races. So the way I'm passing my data from inside of IDL is through these variables. And so I define my little module here, and then or my little function or whatever, and then I am going to then call it. So once it's been defined, then I just call it through this dot notation. So define CUA, and then now I just do python.cua, and I pass in these arrays from above. It returns a big array to me, and then I take that and I just create a new spectral library, and then I write it out. So this is what the IDL code looks like. You can run it from inside of here just fine. However, I'm going to create a little model using this code to make it a little bit more generalized and a little more maybe easier for users that aren't so familiar with coding. So let's say I'm working with someone else and they say, oh, I really want to try this technique. Maybe I can put this together and then I can say, oh, here's your building blocks. So the way that works is, let me flip back to my presentation. I've got a couple of little graphics we can take a look at. This will get out of the way. There we go. All right. So this is going to be the end result, but how are we going to get there? So we've already talked about our code inside of IDL, and we've talked about how ENVI is going to be running it. But the two pieces that we're going to interact with are the modeler or the task kind of interface here. And so the cool part is that when you write your code in IDL, and then you use this little extra piece called a task document. So it's just it's a piece of JSON that it will build these for you automatically. So when I'm thinking about creating a new tool, I usually think about three things. So I want to define my input data, I want to run my tool, and then I want to package up my results. And so just like what we saw before when we were looking at the code, this is the exact same code, but once again, I'm defining my inputs, I'm running my tool, and then I'm going to package up my results and get them out. So it's not a lot of code. I really want to stress that, like, yes, you do have to know how to code to be able to do these sorts of things, but it's not an insane amount. You don't have to be an expert. You just have to kind of be able to follow a methodology and put a few different pieces together. So here's it all together. And then the last piece that I was talking about, the task. So this is what that looks like. So this is just a list of instructions that essentially tells ENVI, hey, I'm going to run this program, and the inputs that are going to go into this program, they are going to be in a really specific format. So the input, let's say I'm going to have an input of my spectral library, and I'm going to tell ENVI, if I use the variable name spectral library, you can assume that that's going to be an ENVI spectral library. And so by telling it what it's going to be ahead of time, then it can build all those interfaces, and it can also help make all those connections and everything so that it can be used inside of the ENVI modeler. So the ENVI modeler allows you to use ENVI task to be used as building blocks for creating custom workflows. It also automatically builds these little GUIs for you so that you can interface with those. And then it also does parameter validation. So it's very nice if you put together your IDL code with the ENVI task. You pass it into the folder, because on the other end you get the little modeler blocks and the little tasks as well, like little GUI. So let's jump back over here and we'll take another look at it. All right, so this is the unit vector that we're going to use, or the unit absorption spectrum that we're going to use. And so let's look at it in a model. All right, so I already have the model built, so I'll just open it. And we'll actually take off this last piece here just for now. And so, all right, we have our Avarice next-gen image, and then we have our methane spectrum that we're going to be looking at. We're going to convolve them together so that then the methane spectrum looks as though it was imaged by the Avarice sensor. And then we're also going to, we'll save this off to a file. So we'll save it off to our temp directory. All right, then we'll click run. All right, and now it's done. You saw the boxes kind of light up. That was as they were running. And so let's go take a look at it. All right. This is over in my temp directory. Oops. Where did it go? There we go. All right. Let's grab, we'll put it all in a new plot. Make it look nice. Let's grab this one first. So this one is going to be our original methane absorption spectrum. And then our new one, so let's see. And then we can bring in our new one. Do a nice color, make it pop out. There we go. And then we can even put a legend on it so we know what we're looking at. All right, so now we have our methane unit absorption vector, or unit absorption spectrum convolved to look like Avers. And so that's what we're going to use from here on out. So just to recap, we used ENVI, we called out to Python through just that little piece of code we wrote inside of our IDL script, and then we got our results back. And those were all just passed around as arrays. So next piece is, let's do the match filter piece. So the match filter is going to take our methane signature and then our image, and it's going to do a convolution together and to bring them into the same space. And it's going to then produce a concentration per pixel. So you can think of match filter as just usually it's a good, like a representation of how well the signature you are looking at fits. However, because of the math that was presented in these papers, this now can say, well, no, it's not just how good it fits, it's actually the amount of methane particulate per pixel. And so that's what we're going to take a look at. All right. So we're going to do the exact same thing that we did before. So we can use the modeler or the task, and we're going to call through ENVI, through IDL, and then out to Python. So but this time we're going to use an entire module inside of Python. So this is how we're going to do it. We're going to define our inputs once again. So we are just grabbing the name of the file that we're interested in, as well as the spectra that we are going to use. So this is our Avers next gen scene, and then the spectra that we just created. And then we are going to figure out the current directory that we're working in. The reason that that current directory is important is because I've saved my Python code alongside my IDL code, alongside my task, and they all are in the same place. But when I get ready to run my Python code, I need to tell Python, hey, go look in this folder. This is where the code that I'm going to run lives. And so that's what those first few lines are. It says Python, append the directory that I'm in to your path. And now Python, go out and find my match filter example. And then the next bit is going to say run my match filter example. So it's going to pull in my header file, my image file, and my spectrum. And so the reason that it is using the header file and the image file is the code that was provided to me uses a library called Spectral, which is a Python library, and they have a whole bunch of tasks and things in there that will read in an image and pull out all the metadata that it needs and run. And so the code that Phil and Marcus had created had already had this all in place. So I didn't really want to change a lot. I just wanted to use exactly what they had. And so I just passed in my file names. And then the results will pop out and I'll create a new raster from it. And that's it. So looks like this. So I'm going to take my image of my spectra, pass it into this Python code and get my results out. So the only difference here is because I'm not writing my Python code inside of my IDL script, I'm going to write it outside. So I just need to make sure that that file is included. And I have my custom code folder here. So this is a folder that ENVI recognizes. And so that's where I put all of my code so that ENVI knows when it goes to start up, it should look in that file and see if there's any programs in there. So let's go take a look at what we got going on here. All right, so we have our spectra. and it's now in the same wavelengths and same everything as our Avers Next Gen scene. And so we will use another model, actually the same model, to create that methane image. So when I wrote my, if we go back over here and take a look at this piece of code, the match filter example, this is the piece of code that we were just looking at. And then it's got this task file that goes along with it. And inside of the task file, there's this little block up here that says tags, which can make it really nice if you're writing custom code, because this essentially just groups everything together. And so because it has that little piece in there, when I'm inside of my model builder, I can look at the little button that looks like a tag. I can go to my methane example, and then it says, oh, you have these two tasks that sit inside that little subfolder essentially. And so I will add that over here, connect the two boxes, and then I'll put the results out to the view. We'll take a look at what we got. So let's give it a run. Oops, forgot my input raster. Connect that over to that box. Oops. Didn't like. Live demos, you know? Try it again. Well, let's try it this way. So we'll look at the run task over here. And then we have our, oops. So this is that. So when you create your tasks, it will also generate this little user interface for you. So this little GUI, it does it automatically. You don't have to do anything special, which is really nice. Now, let's use this. Let's see if this will work. We'll put our output raster. I promise you, I ran this so many times before this demo. Let's close it and reopen it. Let's pretend like that didn't happen. All right, maybe I ran it too many times and it was like, nah, I'm not gonna do it anymore. So these are the results that we get back. So each pixel in the scene represents the parts per million per meter. And so you can see the white areas, and that would be areas that have higher concentrations of methane. And then you can see the darker areas, and those are areas that have lower concentrations of methane. We can stretch this to make it a little easier to see. So we'll go anything above 0, and then we'll go up to a high number, let's say like 3,000. So now you can see the areas that are producing it, and you can also see the clouds that are coming off of it. So for example, this area right here, we can do a quick color mask on it. Let's switch it so that it looks more intense. Go back to the 0, 3,000. Oops. All right, so now you can see methane coming out here. Since we have our scene right underneath, let's do a little transparency. And you can see it coming out from what appears to be maybe a smokestack or something. So, but yeah, we've done it. We've essentially, the intention was to show that we could take ENVI, which we're in right now, take somebody's code that we really have very little knowledge of, but we just want to try it out, but we feel really comfortable in ENVI, run it through, use two different interfaces. So we ran it through this one, so the little task interface, and then we also did it through the modeler as well. And so those are your two main entry points into your code, at least from a graphical user interface. So this is looking good to me. So now let's take a look at what else we got over here. All right, so there we go. There's the results. So the last bit, final display. So let's make a product that we could pass along to somebody, or maybe we could put a picture in a paper that we're writing. So the last piece kind of in that processing chain, final QA, QC, as well as some product generation. So we're going to do that once again inside of ENVI. And this time we're not going to use any open source tools. We're just going to use the building blocks that come along with our ENVI installation. So I made this little model down here. So I took my methane concentration image. So just like we were looking at before, I then threshold that image so that I get just the areas of high concentration. I smooth those regions so that I just get kind of that plume, and then clip my image and colorize it. So let's go take a look at. So right now we have this. It looks nice, but it's maybe we could tighten it up a little bit, maybe make it a little bit more eye-catching. So let's run that model and see what we get. Here's that model that we just showed. No, whatever. I obviously have done. Oh, there we go. All right. Oh, it was trying to warn me. It was like, you don't want to do this. So we will do our. We'll let it run the same one, but then classification results.
I think you might have named your raster incorrectly. I think you might have spelled it wrong.
Oh. That has never happened. I have never spelled anything wrong. Let's say, we'll use this guy. I joke, I have a challenged relationship with spelling. I think there's some people on the call that know me personally, and they probably can attest to that. So let's try this. All right. So now we have these beautiful little clouds. Thanks, Megan. So we have now clipped out the regions in which are just those high concentrations, and we can then colorize them however we'd like. So I'm going to use the same color ramp that I used before. And I'll flip it again. And then I'll let it do its own stretch. And then I'm going to create my true color. I'll drop my little mask on top of it. And there we go. Now we have what I would classify as an eye-catching graphic that we could present, send off to somebody, put in a paper. You can also analyze it, obviously. That's the whole purpose of it, but it's also nice to make it look pretty. All right. Last but not least, you can take all those steps if you want, put them all into a big model. So you can go from raw image and spectra on the left-hand side to product ready graphic on the right-hand side. And we did it through, so ENVI opened all of our images for us, allowed us to get the data that we needed. This is where the Python code is running. So we're both writing the code inside of our IDL code, as well as calling out to a whole library. And then this is where we run our ENVI cleanup steps. And so, yeah, this nice little path here also is now generalized enough that if we wanted to, if we had a new spectra on the left, as well as a new image, we could drop them in, rerun it, and get the results out on the right-hand side. All right, so that's kind of all that I had. I think there's been quite a few questions that have popped up, and I'd love to help answer some stuff if I can.
Thank you so much, Austin. This was a great just entire workflow. And related to that, a question that's popped up a bit is, can people have access to this code?
I would say yes. Let me, since I actually didn't write the algorithms, let me double check with the authors once again that they are fine with me distributing this before I give any permission or anything. But from my perspective, yes. But it is their work. They did all the heavy lifting, so they may want to run through you guys. But yeah. But yes.
Fantastic. Just yeah. So the PowerPoint will be available after this as well, and then we will follow up to see if. Because yeah, there were quite a few people who are like, "Ooh, I wanna play with that too." So
terrific. Yeah, I think I was really excited about it because not only is it an amazing example, shows off something really cool, but it also like I think it was like a really discrete learning example as well. So hopefully, if you've never done this before, you could see the pieces, walk through it on your own. You also get some cool science out of it. So I think it's pretty awesome.
People are definitely agreeing with that. Another question we got is, where can we get that methane absorption signature?
So that was generated. So that yeah, keen eye. So that that was generated by the authors. So there is some work that goes into that because it is pretty much scene dependent. So you can imagine if you have a methane plume or something sitting in your atmosphere, and then you were to image it straight down, or if you image it over here, you're passing through more atmosphere and then hitting it. And so because you're modeling all of these pieces, you need to model where the sun is and where your aircraft is and how high you are, and then you also need to put in methane. So I believe the authors they created that using Modtran, and they produced it. So I think they walk through it in that paper. So if you want to replicate how they did it, you can go to that paper and check that out. But yeah, it wasn't something I covered in this because it's just an extra step. So yeah, I apologize because I essentially started with the magic set of like, here's my two great inputs and let me just put them in. So it's part of the fun though.
Yeah, that is. It's showing how the entire system works.
Exactly.
And let's see. So thank you for that. Hopefully that did answer the question. So this is sort of a general question, but someone asked, can you identify the significant bands which highly correlate with an objective? So this is sort of more of an ENVI overall question, but does sort of relate to the talk that you did today. So like, how would you go about doing that?
Oh wow, yeah. So there's so a whole host of different ways you could do it. So like you saw here. So this in this example, so obviously these spectral regions highly correlate with methane because they took an atmosphere, they then increased the methane absorption in it, and then they looked at the change essentially between the two. And so you can say, oh, okay, these spectral ranges between like what is that, like 2200 and 2450, as well as like 1700 or 1600 and 1700 are the ranges that methane is going to have a really high correlation between your signature and the actual material that you're looking at. So that would be the first one. Just look at the spectra and be like, is there something weird about it? Like, what do I see here? Another way you can do it, so inside of ENVI, you could, if you don't know a whole lot about your scene, you can run a PCA. So PCA is principal components analysis. And so that looks for like kind of like the highest variability essentially. And then you can go back and say like, oh, it looks like my target lit up in this crazy color, this crazy way. And then you can kind of back it out and say, well, what bands went into weighting that? So you can do the math kind of backwards and figure that out. You can like yeah, I mean that's like that's like the Pandora's box question, because then you're like, well, then you can do all these like end member extraction techniques to go and try to find your optimal end members, and then once you have your end members, then you can start going and looking at the spectra and figuring out what is unique about these end members that helps define this. So yeah, I mean that's like almost like the basis of remote sensing is like, how do I get a representative signature that will then help me find my target in my image? And so they have like multiple books that just talk about it. So
you could just read out one of the books for the rest, just like go through all the different examples.
exactly. So, but yeah, there's also, I mean, there's so many, there's so many different ways. Yeah, so yeah, sorry. Hopefully that gave you a little bit of a taste. Look at the spectrum, look at the bands that go into it. So.
Yeah, and yeah, there's a lot of tools for doing that. You might find some more your style than others. Austin listed off quite a few, but there are always more. They're always being created too.
Yes, yeah, exactly. Yeah, if you see something amazing that somebody made, try to get a hold of it and try to run it in ENVI.
Related, great segue, Austin, because you worked sort of with a combination of things here. What kind of packages in Python have you seen people use with ENVI, or do you think might be cool to use with ENVI and IDL?
Yeah, so there are a ton. So Spectral is a good one. There's also another one, Pi-hat. That one is used in the kind of like I don't know. They use it a lot on other planets. So like the Mars rover, the different hyperspectral sensors that are orbiting Mars. So they use that with those. Then you have like standard stuff that a lot of people use, like GDAL. You can use, so there's a toolbox called Orfeo that has some neat tools in it. There, I left it out, but one thing I was going to do, there's a package called 6S, which is a radiative transfer model package that runs really great through Python. So you can give it you can have it generate your atmosphere for you. There's Yeah, I mean, like, so like scikit-learn, that one's like kind of a standard one. Same with like NumPy. You can get, the nice thing is that open source has so many tools, so you can start to kind of navigate however you want. So like you get your data into an array, or even you get your results, and then you can do all sorts of different data manipulation. So you can use pandas. They're really great. So yeah, there's
Pandas are really great.
those things. Yeah.
Let's see. We have another question, and this one is, I will also post a link for this in chat, but where can I find more info on using the Python bridge? And can I call utilities in other languages like R?
Yeah, so so a long time ago, so we don't have a direct bridge to R. A long time ago, I wrote some code that actually called through the Python bridge to Python, and then Python has an R bridge. So I went IDL to Python to R to Python to IDL. So it's not super elegant, but you can do it that way. There's also inside of IDL, there's a spawn command, which essentially allows you to just run any kind of like command line argument that you would, or whatever command that you would want to. So if you have some sort of code that you can run from the command line that's just like a one line, you can spawn it from inside of IDL and then get the results back. You once again have to figure out like, how do I get my data into it and how do I get my data out of it? But yeah, you can definitely do that. You can also run, so you can run C code from inside of IDL as well. So.
Nice, thank you.
Mm-hmm.
Let's see. And I have also posted a link to our Python IDL bridge webpage in chat. So if you want to go and see that as well, that is available too. And let's see. I think we have time for one more question before all the closing remarks. Let's see. Trying to find a good one to end it on. I guess in the end, why you sort of went over this briefly, but we didn't, why are you doing pre-processing in ENVI? Like all that pre-processing and stuff, why did you decide to do that there?
Oh, I think actually, so why did I opened my imagery in ENVI and then I passed it over. I did like I convolved the spectra to make it look the same, but I did that in Python.
Mm-hmm.
You couldn't do it in ENVI. The authors of this paper called out that they wanted to use the band centers as well as the full width half max so that they could replicate it as close as possible. And so they had their own special sauce that they were like, I really like this. This is how I want to do this to make sure that my bands line up. And so I just replicated what they did. But yeah, you very much can do it inside of ENVI.
Great, fantastic. So, thank you very much.
Yeah.
Thank you, Austin. This was a great overview and just going through the entire process step by step with a live demo, which are always a little, if you've ever done a live demo, they're always nerve-wracking because it can work perfectly. And then the instant that camera turns on, it's like, oh no, what's happened? My computer's turned off, the cat sat on the power button. So thank you very much for doing that.
Of course.
Yeah. Before I close out this entire session, there is something I want to bring up. And that is yesterday. So if you guys have been following the Spectral Sessions and learning all this stuff, maybe you've used spectral stuff all your life. You're the master of multispectral and hyperspectral, or maybe you're just getting started and you're just sort of learning and trying to get all the stuff. And a lot of the words that were used today might have gone over your head, or things you're like, I've heard that term before and I'm not too sure. We did just release yesterday the what we're calling the e-learning. So this is in chat as well. It is apparently not a link, but it is actually a link. And so these are self-paced training courses that have been developed on just understanding and analysis of workflows for just everything spectral. If you're interested and you want to take a look, please go check out that link that's available. They're pretty cool. There's been a lot of work that's been put into them to try to make them so that they're understandable and teach things at every level. And with that, I'd like to thank all of you for being here. Austin, thank you again for presenting today. And I'd like to thank everyone who's been involved with Spectral Sessions. We have Abby and Matra hidden in the background this entire time who've been making sure everything runs as smooth as possible. And all the other presenters, speakers, and all of you guys, thank you for being here for all this stuff. Make sure to get your swag. There's some pretty cool stuff out there once again. And this has been recorded. You will be getting the PowerPoint slides. And thank you all for attending Spectral Sessions. That's all, folks.